Have you ever just stood and watched a thunderstorm and really wondered, how does that happen? How does a simple cloud, just a bunch of water and ice, unleash something as powerful as a lightning strike? Well, today, we're going to pull back the curtain on the incredible science behind nature's most epic light show. So, let's just start with a big question right up front. How does an ordinary fluffy-looking cloud manage to turn itself into a massive floating power plant? Seriously, one that can generate millions of volts of pure electricity. That's the puzzle we're putting together today. All right, our journey begins way up there, inside what you can basically think of as a factory in the clouds. Because that's exactly what a big storm cloud is. It's this chaotic, swirling factory that's just churning out electrical charge. And for this factory to get going, you need three key ingredients. You need tons of tiny, lightweight ice crystals. You need heavier, super-cooled water droplets, sometimes called soft hail. And then you need these powerful updrafts, these winds just rushing upwards, mixing everything together. It creates this incredibly violent, turbulent mosh pit high up in the sky. Now, all of that bumping and crashing around up there, that's not just random chaos. It's actually the engine that kicks off our next step, building a giant battery right there in the sky. This is where the cloud really starts to generate and, more importantly, store a huge electrical charge. The science behind this whole thing has a fancy name, the tribal electro effect. And I know that sounds super complicated, but I promise you've seen it. If you've ever rubbed a balloon on your hair and then stuck it to the wall, yeah, you've just used the tribal electro effect. What's happening in that cloud is pretty much the exact same thing. It's just static electricity on a mind-blowing scale. So picture this. Inside that chaotic cloud, you have these light ice crystals being pushed upwards by the wind and heavier little hail pellets or graupel that are falling down. And every time they collide, bam, electrons get knocked off. The lighter ice crystals end up with a positive charge, and since they're light, the updrafts carry them all the way to the top of the cloud. Meanwhile, the heavier graupel has collected all those extra electrons, making it negatively charged, and gravity pulls it down toward the bottom. And here's the result of all that sorting. The cloud is now polarized. You've got a positive pole at the very top and a negative pole at the bottom. It has literally become a giant battery floating in the atmosphere, just building up more and more potential energy. But here's the thing. The cloud isn't working in a vacuum. That immense electrical field it's creating has a huge effect on the ground right below it. So let's take a look at how the ground itself starts to respond. So as that super strong negative charge builds up at the bottom of the cloud, it starts pushing away the negative charges on the surface of the Earth. It's like magnets repelling. This leaves the ground directly under the storm with a shadow of positive charge. And now you have this invisible, crackling electrical tension connecting the sky and the ground. Okay, the stage is officially set. All this tension has been building up between the cloud and the ground. And now we get to the main event, the spectacular flash and that unforgettable roar. You see, air is actually a really good insulator. Electricity normally can't just flow through it. But the electrical difference we're talking about here is so huge, so powerful, that eventually the air just can't hold it back anymore. The insulation fails. It completely breaks down. And when that breakdown happens, the energy that's released is just staggering. A channel of plasma, which is what a lightning bolt is, instantly superheats the air around it to about 30,000 Kelvin. Just let that sink in for a second. For a fraction of a second, that narrow channel of air is hotter than the surface of the sun. I mean, that is the kind of power we're dealing with, unleashed in a blink of an eye. So, what is thunder then? It's not actually the sound of the electricity. It's the sound of the air violently exploding. That insane heat forces the air around the bolt to expand faster than the speed of sound. That creates a massive shockwave, and that shockwave is what our ears hear as thunder. And this all leads to something we'd all experienced, right? Because there's a huge difference between the speed of light and the speed of sound. Light is so fast that for us, it's basically instantaneous. Sound? Well, sound takes its time to get to us. It's much slower. And that simple little fact of physics is it. That's the reason for the delay. You see the lightning flash the exact moment it happens, but you have to wait for that slower moving shockwave, the thunder, to actually travel all the way to your ears. So as we wrap this up, let's try to bring this massive, almost cosmic process back down to a scale that makes perfect intuitive sense. Let's just call it nature's static shock. I think this quote just nails it. The fundamental physics behind a terrifying, gigantic lightning strike is the same as that little zap you get from a doorknob on a dry day. It's all the same stuff: friction, separating charges, and then a sudden, rapid discharge. And that kind of leaves us with one final thing to chew on. We've just seen how a cloud can act like a giant, natural battery, storing up all this potential energy before releasing it. It really makes you wonder, doesn't it? What other forces, what other systems out there in the natural world are just slowly, quietly building up pressure, just waiting for the right moment to discharge?